Hello, AP Stats. Okay, here we are, Chapter 4, Designing Studies. And I've been working hard today to try to get this ready to go for you, so I'm hoping everything will work. So, first of all, let me get this out of the way. You have your notes that you should have printed out about designing experiments and that you should have gotten from my website. And first of all, we're going to look at differences between an observational study and an experiment. And it says at the top of your notes, an observational study cannot establish cause and effect relationship. Very important. However, in an experiment, we will actually do something to individuals to observe a response, allowing us to establish causation. So if it's a well-designed experiment, we can actually say, wow, it looks like X causes Y, instead of before where we might notice a relationship but not necessarily be able to say that there's causation. So get down in your notes, and experiment deliberately imposes some treatment on individuals to measure their response. Now make sure that the treatment is something that would affect a response. So it's doing something to the individuals to be able to get a response. An observational study, you still might be doing something to the individuals, but it's not in order to affect their response. It observes the individuals and measures variables of interest, but does not attempt to influence the responses. So make sure you know the difference between the two. Our goal is to understand cause and effect. Experiments are our only source of fully convincing data. The distinction between observational study and experiment is one of the most important in statistics. Make sure you know the difference. Okay, our next definition here is experimental units. They're the smallest collection of individuals to which treatments are applied. When the units are humans, we'll call them subjects. So experimental units can be anything that we're doing an experiment on. It can be humans, it can be turtles, it can be rocks, it can be streams of water. So, but make sure it is the smallest collection which is actually getting each treatment. And so on to language of experiments. So much vocabulary in this chapter, so make sure you know the difference. An experiment is a statistical study in which we actually do something, like we said, a treatment to people, animals, or objects, the experimental units, to observe the response. So we're going to, again, have a explanatory variable and response. A specific condition that the individuals are going to have on them is the treatment. And if an experiment has several explanatory variables, the treatment is a combination of those. So for instance, your treatment might be, say, to see if SAT scores are going to improve. So the treatment might be a combination of explanatory variables. Maybe these people are going to eat a better breakfast as well as take an SAT prep class. So both of those things are explanatory variables, but together they make up the treatment. So make sure you know the difference between the two. Sometimes the explanatory variables in an experiment are called factors. Okay, factors, explanatory variables, basically means the same thing. Many experiments study the joint effects of several factors. So really, factors and explanatory variables are pretty interchangeable words. In such an experiment, each treatment is formed by combining a specific value, often called a level, of each factor. So if you have an explanatory variable, for instance, Tylenol, and maybe you're going to give one group 1 Tylenol and another group 2 Tylenol, those would be the levels of the same explanatory variable, the same factors. So your treatment is made up of factors, also known as explanatory variables, and sometimes different levels of those factors. Okay, this is not right in your notes, but this is very important. We've talked a little bit about lurking variables. It's a variable that's not among the explanatory or response variables, but it's still influencing the response. So this is something that often allows us not to be able to see a causation relationship because there's some variable in there, like, say, genetics, or we talked about the example with population increasing and causing two things to change the same way at the same time. So an experiment seeks to control these lurking variables. So here's an example on page 236. So pause the video just a second and flip to page 236. Okay, in your book, it talks about an SAT example. A high school regularly offers a review course for the SAT. This year, budget cuts will allow the school to offer only an online version of the course. And over the past 10 years, the average SAT was 1620. The online group gets an average score of 1780. That's roughly 10% higher than the long-time average for those who took the classroom review. Is this online course more effective? Okay, so we're looking at this experiment here, and first of all, I want to show you kind of how you will map out an experiment. We'll often just draw them out like this, experimental units, and in this case, our experimental units were our test takers, or people who were taking the online course and taking the SAT. What was the treatment? And you will write out what exactly that treatment was, which was taking the online course, and what response was measured. And here the response that was measured was the SAT score. So students were the experimental units, also known as subjects. Online course was the treatment. The SAT scores was the response that would be measured. A closer look showed that the students in the online review course were quite different than the students who took the classroom course in the past years. They had higher GPAs. So there were some lurking variables there of GPA that was affecting that response, not just the online course. So you couldn't really find causation there. So there wasn't good control. Would be much better if we had taken a study where we had divided randomly two groups of experimental units into two treatments, one in the online course and one in the treatment, and therefore hopefully it would spread out those differences in GPA and therefore be able to see more of the measurable response and make a better conclusion. So that brings us to, what are those important 3 principles of experimental design? You need to know these backwards and forwards and be able to discuss them. A randomized comparative experiments are designed to give good evidence that differences in the treatments actually cause the differences we see in the response. We're going to call these CRD, a completely randomized design. And you can use this abbreviation when you're talking about your experimental design, and make sure when you're talking about your CRD, you address how did you meet each of these principles of experimental design. So first of all, control. We need to control for lurking variables that might affect the response. And control comes in a couple different ways. Sometimes you're just controlling the environment. Maybe if you're comparing 2 colas, you make sure that they're in the same types of cups, that they're going to look alike. But even more importantly about control is there has to be a comparison, like we talked about with the SAT example. You have to have 2 groups to compare to make sure that the only systematic difference between the 2 groups is the treatment, not something else that was already there. So the main principle here coming from control is make sure you have 2 groups or multiple groups to compare, as well as controlling other variables. Secondly, very important, is random assignment. Using personal chance to assign experimental units to treatments. Now notice, sample design, we talked about randomly designing samples, randomly getting people to do something. But here, we already usually have volunteers, and we just want to randomly decide which treatment that they are going to be in. This helps create roughly equal groups of experimental units by balancing their effects of lurking variables that aren't controlled already. So we've controlled what we can control with our first principle, but random assignment will control those things that we can't control, perhaps genetics, others IQ, depending on what experiment we're going to do, things that we can't actually control. If we randomly assign them to treatment, this should decrease some kind of natural bias that might be in one group than another. And the third one is replication. Replication is just, doesn't mean do the whole experiment all again, which of course would be good if you could, but use enough experimental units that in each group, so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. So in other words, if you do an experiment and you just do it on one person takes Tylenol and one person takes Advil, and the Tylenol person gets better quicker, you can't really come up with a good conclusion unless you've done it on enough people so that you can tell the difference isn't just from natural variation. You are still going to have a natural variation in your data, but this decreases the effect of that natural variation. Very important, those three things. So when we look at our completely randomized design, the treatments are assigned to all the experimental units completely by chance. Some experiments may include a control group that receives an inactive treatment, or maybe just a baseline treatment that already exists. Remember, a control group is what you're going to use for your comparison, and it might be a group with a placebo, but not necessarily. So here's how you might draw out your and you can, when you're explaining an experiment, you can do it in a diagram or maybe in a paragraph. So you tell me who your experimental units are. So perhaps they're 100 males in the United States or something like that. Then you tell me, how are you going to randomly assign them to different treatments? Are you going to use a random number table and pick 50 that are chosen, go into group 1, and what is that group 1 going to do? Suppose they're going to take 2 aspirin, and group 2 is going to do something else. They're going to have 2 Advil. Maybe aspirin was the old treatment, and you're trying to see if Advil, the new treatment, is going to be better. And so these are the 2 treatments that they're in. Those should actually go there. And then after, in your results, make sure you measure some kind of results. Suppose we're going to ask their pain. We're going to measure their pain relief. So maybe there's a pre-measure we take before and ask them to rate their pain, headache pain, from 1 to 10, and then we measure that again on the results. So this is how you would kind of map out what an experiment might look like. So here's an example. Turn to page 241, pause the video, and read that description as the physician's health study. And here you have factors and levels of an aspirin and a beta-carotene. And then we also have a placebo, which is a dummy pill. So there's a lot going on in this experiment. And they ask us, how are the 3 main principles of design used in this? First of all, we have replication for sure, because there were, let me look, I think there were 21,996 subjects in the experiment, and they were put into these different treatment groups here in the boxes. And so there were over 5,000 subjects per each treatment group. So that's definitely a good replication so that natural variation will be spread out to really see a good result from this. And then they do state that there was random assignment from these people into each of these treatment groups, so there won't be any kind of natural bias of one group over the other. And for control, things that they did to control, they had people on the same schedule as far as when they were taking the pill, as well as they had all these different groups, as well as a placebo to compare the results. You had the placebo pill and the aspirin. You had the placebo beta carotene and the beta carotene. And so when you mapped it all out, you could really get a good comparison and not have to worry about those lurking variables of maybe if someone knew what they were taking, they might respond differently. So what can go wrong? Your book talks about the placebo effect. Sometimes a person will think that they are getting better just because they know that they're taking something. So a response to a dummy treatment is called a placebo effect. The strength of the placebo effect is a strong argument for randomization into an experiment. And make sure you know what double-blind and single-blind experiments mean. In a double-blinded experiment, neither the subjects nor those who interact with them and measure the response know which treatment the subject has received. So make sure you know for double-blind, single-blind is that the subject doesn't know which treatment they've received. And this is also part of this are the people that interact with them. If the doctor or whomever is interacting with the subject makes it clear to them which treatment that they're in, it's really affecting the subject's knowledge. The second person is the person that measures the response variable. So this might be the interviewer, this might be the statistician. The person that's actually measuring the response variable is the second person that needs to not know which treatment is which. Of course, somebody has to know, and that's usually the person that's implementing the study, but not necessarily the person that's measuring the response variable if it's to be double-blind. The last thing you need to go over is blocking. Blocking is a way to improve a design. It is not the same thing as a completely randomized design. A completely randomized design, you're randomly putting people into treatment. Blocking is when you go ahead and separate people into groups or subjects or experimental units into groups that are similar. So maybe, for instance, you are doing a study with drugs, Tylenol, and you think perhaps that male and females will react differently to these drugs. So you block at the beginning and put females in one group and males in another. And then within those blocks, you randomly put half of those females into the aspirin group and half of those females into the Tylenol group. And then with the males, you do the same thing. Have half of the males be in an aspirin group and half of the males be in the Tylenol group, so that each block gets every treatment. And then we compare the response variable within those blocks and then amongst each other and see the different effects. That's a randomized block design. One special kind of block design is a matched pair design. A matched pair design is when you're comparing two treatments and you either have matching pairs, creating blocks that are exactly alike, meaning like two people that would be exactly alike in some type of characteristic, or you have the same person or same experimental unit do both treatments. Chance is used to determine which pair gets each treatment or which, if you are doing both treatments, if I'm going to take a pre-test and a post-test, for instance, and those are the two treatments, that would be a matched pair design. And I might flip a coin to see which one that I do first. So I still need to randomly decide which one I do first. That's all for tonight. Hopefully you will fill in the quiz for me and get that to me, and I will see you tomorrow.